Standard network routing relies on careful calculation. A router acts like a highly efficient traffic cop, consulting complex internal tables to find the single best path for a piece of data to travel. But consider what happens when the network itself is physically unstable. If nodes are constantly moving or hardware is actively being destroyed, those carefully calculated routing maps become instantly obsolete. When precision calculation fails, engineers turn to an extreme alternative known as network flooding. In high-stakes scenarios, the only way to guarantee a message reaches its destination is to abandon the concept of efficiency entirely and rely on absolute brute force. The underlying rule of flooding is startlingly simple. When a router receives a data packet, it sends an identical copy out on every single outgoing line, except the one it just arrived on. This approach creates a mathematical guarantee. If a single unbroken path exists between sender and receiver, the packet reaches its destination. But there is a fatal flaw. Without strict limits, these routers will pass the exact same packets back and forth infinitely. This creates a feedback loop called a broadcast storm. Within milliseconds, the network generates millions of duplicate packets, exhausting bandwidth, draining CPU memory, and causing the entire system to crash. To actually harness the power of guaranteed delivery, engineers have to put a leash on an algorithm that desperately wants to destroy the system. The first control mechanism they deploy is an expiration date, formerly known as a hop counter. Every time the packet passes through a router, that counter drops by exactly 1. The moment the counter hits 0, the packet is deleted. Engineers initialize this counter to match the full diameter of the network, ensuring the packet lives just long enough to cross the system, but no longer. Hop counters successfully stop packets from circulating forever, but they don't solve the immediate problem of routers drowning in thousands of duplicates during those early stages of the transmission. To filter out those early duplicates, engineers give the network a memory. They stamp every outgoing packet with a unique sequence number. Receiving routers keep a running list of these numbers. If a packet arrives with a sequence number that is already on the list, the router knows it's a duplicate and simply throws it away. However, in a busy network, this tracking list grows infinitely long, eventually consuming all of the router's available memory. The solution is a clever mathematical compression known as the K-counter. Instead of tracking a massive scrolling list of individual sequence numbers, the router tracks a single variable, K, which represents the highest contiguous sequence number it has seen. This single variable allows the router to assume all sequence numbers below K are already processed, meaning it can efficiently drop old packets without suffering a catastrophic memory drain. The third and final fix applied to this system is selective flooding. Instead of routers firing packets blindly in 360 degrees, they analyze the network topology. They only forward packets down lines that are heading approximately in the right direction of the target destination. By combining expiration dates, the memory compression of the K-counter, and selective directional logic, the chaotic brute force flood is tamed into a precise engineering tool. Because flooding still consumes significantly more bandwidth than standard routing, its deployment is reserved exclusively for extreme environments. You will find it hardwired into military ad hoc networks, where radio nodes are constantly moving across unpredictable terrain and demand a communication protocol that simply cannot fail. This diagram shows the architecture of a massive distributed database system. Flooding is used to push updates through these interconnected primary and backup clusters simultaneously, ensuring thousands of geographically separated sites hold the exact same information. It serves as the bedrock protocol for systems where the cost of a missed message is total system failure. Beyond its practical applications, flooding serves as the theoretical gold standard against which all other routing algorithms are judged. Because flooding duplicates itself to try every single available path in parallel, no other algorithm can mathematically reach the destination with a shorter delay. The algorithm demonstrates a simple truth. The most effective way to navigate a maze is to fill every possible path at the exact same time.